This lesson has been developed in the framework of SCILED project. Module 3, Footwear Design Engineering, Unit 2, Introduction to Materials Engineering.
Lesson 2.1. Introduction to Materials Engineering. This lesson is structured as follows.
Introduction. Classification of materials. Basic shoe materials. Determination of mechanical properties.
Introduction.
Materials affect every part of our daily lives in one way or another, such as transportation, housing, clothing, communication, recreation and food production. It wasn't until relatively recent times that scientists came to understand the relationships between the structural elements of materials and their properties. An advancement in the understanding of a material type is often the forerunner to the stepwise progress of a technology. Virtually all important properties of solid materials may be grouped into 6 different categories: mechanical, electrical, thermal, magnetic, optical, and deteriorative. In addition to structure and properties, 2 other important components are involved in the science and engineering of materials, namely, processing and performance.
The interrelationship among processing, structure, properties, and performance is as depicted in the schematic illustration. Classification of materials.
Materials can be classified into 4 broad families: metals and alloys, ceramics and glasses, polymers and elastomers, and composite materials. Metals are relatively stiff and strong, yet are ductile, and are resistant to fracture. Metals are extremely good conductors of electricity and heat. Ceramic materials are relatively stiff and strong. Ceramic materials are typically insulative to the passage of heat and electricity and are more resistant to high temperatures and harsh environments than are metals and polymers. Polymers include the familiar plastic and rubber materials. These materials typically have low densities. In addition, many of the polymers are extremely ductile and pliable, which means they are easily formed into complex shapes. A composite material is composed of 2, or more, individual materials that come from the categories previously discussed. The design goal of a composite is to achieve a combination of properties that is not displayed by any single material and also to incorporate the best characteristics of each of the component materials.
Basic shoe materials.
The basic materials used in footwear design and manufacture are leather, wood, cork, elastomers, polymers and metals. Leather is used on the outside of the upper part, in the lining system, as an insole, as an outsole and as well as in decorative elements. Some traditional footwear include wooden parts in sole and in the upper, but usually wood is limited to the shoe outsole and heel. Cork can be used as the main material for midsole or outsole. Polyurethanes are widely used as the main material for the construction of outsoles and midsoles in simple and double-density systems and as the main material for the manufacture of foam coatings. Metal stiffness and protection components are mainly made of steel. Metal fittings are also used in fastening and decorating systems. The material's mechanical properties are shown in the table.
Determination of mechanical properties. The mechanical behavior of a material reflects its response or deformation in relation to an applied load or force. Key mechanical design properties are stiffness, strength, hardness, ductility, and toughness. The properties related with the strength of a material are normal stress, shear stress, normal strain and shear strain.
Normal stress occurs when a member is loaded by an axial force. Normal stress is defined as the ratio of the load to the cross-sectional area, where the load is perpendicular to the cross-section. Shear stress is defined as the ratio of the load to the cross-sectional area, where the load is parallel to the cross-section. Normal strain refers to the quantification of the alteration or expansion a body undergoes when subjected to a force or set of forces. The ratio of extension of gauge length to its original length is defined as normal strain. Shear strain is the ratio of the change in deformation to its original length perpendicular to the axis of the member due to shear stress.
The degree to which a structure deforms or strains depends on the magnitude of an imposed stress. Let's consider a bar subject to increasing tensile loading. For most materials, including metallic materials, the initial part of the curve is straight, as shown in the stress-strain diagram in the left figure.
The part O(A) defines the elastic area, elastic behavior, of the material and the part CE the plastic area, plastic behavior. Point B corresponds to the material yield stress, while point C To the lower material yield stress, the maximum value of stress which corresponds to point D, and it is called the material strength limit, ultimate stress. Finally, at point E, we have a material failure or fracture.
A similar shear stress strain diagram can be derived for a shear loaded body, right figure. The stress strain behavior is used to define several material properties.
The Young's modulus or modulus of elasticity E is the slope of the straight section of the normal stress strain. The shear modulus or elasticity modulus of rigidity G is the slope of the straight section of the shear stress strain. These define the relationship between stress, force per unit area, and strain, proportional deformation, in a material in the linear elasticity regime. The relationship between the stress and the strain in the linear, elastic, region of the curve is expressed by the Hooke's law. When a structural element contains a discontinuity, such as a hole or a sudden change in its cross-section, the stresses that are developed near that variation are very large. To characterize the risk of a discontinuity, we define the stress concentration factor as the ratio between the maximum stress and the average stress from the discontinuity to the part surface. At each point in the part, there is a direction in which the shear stress becomes maximum. The maximum shear stress is always half the difference between the maximum and minimum principal stress.
The materials can be classified into three categories according to their displacement behavior: brittle and ductile materials, isotropic and anisotropic materials, and homogeneous and inhomogeneous materials.
Brittle materials receive a very small plastic displacement, and so the energy needed to failure is very small, for example, glass. Ductile materials have very large displacements before failure, for example, soft steel. An isotropic material has identical values of an elastic property in all directions. Glass and metals are examples of isotropic materials. Contrarily, anisotropic materials have different values of an elastic property in all directions. A material of uniform composition throughout that cannot be mechanically separated into different materials is called homogeneous. Homogeneous materials have the same elastic properties in all points. Examples of homogeneous materials are certain types of plastics, ceramics, glass, metals, alloys, paper, board, resins, and coatings. On the contrary, a material having different elastic properties in different points, it is inhomogeneous.
The stress applied in an object can be axial, flexural, bending, or torsional in nature.
In this slide, an example of a three-point bending is illustrated. At the point of loading, the top surface of the specimen is placed in a state of compression, whereas the bottom surface is in tension. The bending stress is computed from the specimen thickness, the bending moment, and the moment of inertia of the cross-section. Torsion is a variation of pure shear in which a structural member is twisted. Torsional forces produce a rotational motion about the longitudinal axis of one end of the member relative to the other end. A shear stress is a function of the applied torque, whereas shear strain is related to the angle of twist.